So my name is Anton Beck. I'm from the Austrian Institute of Technology. I'm a research engineer here, and I work a lot with identifying decarbonization pathways for different industries and coming up with robust ways to integrate excess heat into the process. So my work is mainly focused on internal use of excess heat, and we have or at least I work a lot with optimization-based models to identify those pathways. And that's also why I'm going to present some approaches that we have used over the last years to come up with pathways for decarbonization. And I will try to highlight some of the differences and what we learned from it, basically. And I hope it fits well to the task of strategic planning. So that's why I'm presenting this. So we mainly employ mixed integer linear programming models for our system modeling. So this means we have some restrictions. We have linear objective functions. Usually we're minimizing total system costs, consisting of CapEx and OpEx. We have linear constraints. So our technologies can be only subject to those linear constraints. So nonlinear behavior is always tricky to capture. And we can use continuous and integer binary variables to model our systems. So the binary models are usually for these discrete decisions, whether a unit is integrated into the system or it is turned on, and some operational characteristics like minimal part load and such can be modeled using those variables. And why are we using MILP? Well, it offers a lot of flexibility. We can integrate all kinds of characteristics of the process as long as it's somewhat linear or can be approximated using linear constraints. We can pretty much model realistic system behavior in most cases, and we want to know which equipment to invest in to decarbonize in a cost-efficient way. So typically we have 3 layers that we model. We have an input side where we get energy, different forms from the grid usually, or in the case of district heating, we can also supply heat to those systems. Then we have the local energy system. So classical equipment here would be some natural gas-fired boilers, storage systems, but also renewable systems will be modeled on this layer. And on the demand side, we can go to any level of detail from a basic demand profile, so time series that we need to fulfill, to the actual equipments and the interactions they have. So far, so good. But we don't only want to derive the optimal solution for one case, but we would rather like to identify the pathway from now to the fully decarbonized system, and ideally avoid stranded assets. We don't want to make investments into equipments that we're not gonna use in the fully decarbonized system, or that are drastically oversized because it makes sense for the intermediate step, but not for the full decarbonized system. And so we have used several approaches over the years. And I will give you a short insight. So the first and most basic approach is to calculate cost-optimal systems for different degrees of decarbonization. So we can enforce the system to reduce its carbon emissions by 10%, 20%, up to 100%, and then we get cost-optimal solutions for the intermediate steps. So problems here is we cannot really get the temporal scheduling from it. We don't have the actual years in the back. We cannot really consider some forecasts for capex, like certain technologies will get cheaper in the future with their uptake, and with this approach, this is not easily considered. And also stranded assets cannot be avoided. So for the intermediate decarbonization rates, we might end up with oversized equipment, and as I mentioned before. So we use this for an insulation materials case where we proposed some decarbonization measures and tried to identify the best way to fully decarbonize. And then we get some results like this. So for the individual decarbonization rates, we get the optimal configuration here on the upper figure. It's shown in terms of investment costs. So more investment costs for the same equipment type means larger capacities. And then in this case, we see at 45% decarbonization, we have no more excess heat left. All of the excess heat is used already. And then solar thermal panels get installed more and more to supply the process with additional heat. And then the capacity limit for panels is also reached. So we have another tipping point, and then we can see what's happening there on. So then to avoid this possibility of stranded assets, we came up with some simple strategy to first calculate the configuration for the fully decarbonized system and then restrict for intermediate decarbonization levels the capacities for the different technologies. So no overcapacities would be integrated for the intermediate decarbonization rates. Basically same restrictions as before, but we can avoid these stranded assets. We cannot really come up with a strategy in terms of in year X buy this and that, and also this capex forecast cannot be considered. So we use this approach to identify decarbonization pathways for the pharmaceutical industry. And on this figure that we presented here, we have these different decarbonization levels with the color coding. So the pink one shows the fully decarbonized system, and the capacities they are stacked up. So they are increasing with increasing decarbonization rate. And using this approach, we identified that if pharmaceutical industries is willing to accept some risks for their processes, there's a pretty big potential to reduce their annualized costs, even for relatively high decarbonization rates, because the pharmaceutical industry historically they have not paid that much attention on energy efficiency, but product margins were large enough to neglect this aspect. Then we also considered a one-step approach where we minimized the total system cost for a predefined time frame. So the question was, what is the system minimizing costs from now to 2050? And we used an approach where we looked at the development in 5-year intervals. The process in question was a steel plant of ArcelorMittal, and we used a rather complex system considering also heat integration and integration of heat pumps and integration of heat distribution system on site simultaneously. So it was a pretty big model. So it was steady state within those 5-year time frames. So no fluctuating renewables or anything like that to be included. But what we could do with this model is also incorporate these future developments for equipment costs and also for energy costs. So there were different energy cost scenarios employed, and yeah, we could identify the most robust system, robust strategies for heat integration. So we had these four distinct facilities on site, and the question was, to which extent should they be integrated, looking for a time frame until 2050. Yeah, as mentioned, we defined a lot of scenarios which we looked at, and we calculated total costs until 2050, and we saw that for most facilities, direct heat recovery was integrated, and also a more expensive heat distribution system was considered, even though it was not utilized until 2050. So in the storylines, 2050 was a fully decarbonized system with electrified furnaces, where there was no more or no relevant excess heat potential from these furnaces, but it still made sense. So it was not actually a stranded asset, but something like a transition technology that paid off. And with this approach, we could capture this. Then we tried to do something similar as with the pharmaceutics case, but we wanted to identify actual timings of investments. So here, similar approach. We calculated the fully decarbonized system and then restricted the solution space in between to those capacities. But we used a slightly simplified model with a yearly resolution, and the question was how to minimize these overall costs to reach certain targets for decarbonization, where like there was a decline from 2025 to 2030 in terms of scope 1 or 2 emissions, and this would have to be fulfilled. So I'm just skipping ahead. This is an example of these the results we got from this. So in red there is an investment taking place, and in green this is the annual operation costs, so the mainly costs for energy. And in the slightly transparent view, you can see in the dashed lines, which represents limits for carbon emissions. So the red declining dashed line indicates that the emissions were forced to zero in the end in 2050, and this resulted in investments somewhere along the time frame, and also in the end, I guess there is a fuel switch with a prediction for the energy costs. And then finally, there's one more approach we have employed, where we used a bi-level approach. There was a genetic algorithm, so some meta heuristic used to identify the optimal mix of technologies for the site. And on the second level, there was a linear optimization model that identified the energy mix. And with this approach, we could also identify, similar to the case before, the time when a certain technology should be invested and how the energy mix should look like so that the split between biogas and natural gas and green and conventional power to reach the the targets in the most cost-effective way. Yeah. So the main conclusion I can draw from this is it really depends on what is the actual scope of the project, what are the technologies that could or should be considered, what is the forecast quality. So if we don't know anything about the future, then it's not so interesting to go for this forward-looking approach. And yeah, so I guess this is also on this slide. Yeah, so if there's continuous operation, the models become much more simple. If there's fluctuating renewables, flexible energy tariffs, it gets much more complicated because more different characteristics need to be captured. And also another question, since some of those approaches we have implemented in web-based applications, it's also the question, who is the user? What types of input can you expect from the user? And then usually the more simple model is preferable because the threshold of input generation is too high for a non-expert user. Yeah. So that's basically my insights from the approaches we have used for, I would say, this pathway generation or strategic planning of investments towards decarbonized systems. And yeah, if you have any questions, I'm happy to answer them.